To understand this plot and how it tells us about Earth's climate over the last 66 million years, we're going to have to learn a little bit about what controls the oxygen isotope composition of the benthic forams shell. Okay, just a reminder, so benthic forams, they live at the bottom of the ocean where they grow these shells that are made of the mineral calcite, which has a chemical formula of CaCO3. So that's calcium, carbon, and 3 oxygens. Calcium carbonate, otherwise known as calcite. So how do they grow these shells? Where do they get the calcium, the carbon, and the oxygen? Well, they pull it directly out of the ocean. So if I'm a little foram living at the bottom of the ocean, then I'm going to pull some dissolved calcium. I'm going to pull some dissolved carbon. I'm going to pull those out of the ocean. And I'm also going to have to use oxygen, right? I'm going to pull some oxygen out of the ocean. But this oxygen isn't just floating around as free oxygen. It's going to be locked up in molecules, things like water, and another molecule called bicarbonate, but we won't go into that. But so there's H2O in the ocean, right? H2O is water. But we know that there's 2 isotopes of oxygen. So that means that in the ocean, some of the water is H2O with an 18 oxygen, and some of the water is H2O with a 16 oxygen, right? So depending on which molecule of water or bicarbonate, right, any oxygen-bearing molecule, there's going to be 2 possibilities. Either that molecule will have oxygen 16 or oxygen 18 in it. Now, benthic forams, they grow their shells in what's called isotopic equilibrium with the water that they live in. So that means that the oxygen isotope composition of the calcite shell, right, the oxygen that's in this calcite shell is going to be equivalent to the oxygen isotope composition of the water that foram lives in. Because forams pull their oxygen to make their calcite shells directly out of seawater, and they're in isotopic equilibrium with the with the ocean, that means that the oxygen isotope composition of a foram's shell, right, of the shell, that serves as a proxy for the oxygen isotope composition of the oceans that foram lived in. So it's our first sort of quantitative climate proxy. We have an indirect sampling of the oxygen isotope composition of seawater that ancient forams lived in. Okay, so what can we do with that knowledge? What can we do with the knowledge that our foram shells are telling us about the oxygen isotope composition of the oceans? Well, there's 2 sort of complications or 2 sort of processes that we need to understand in order to make sense of that figure that shows the oxygen isotope composition of benthic forams through time. And the first one of those is a temperature-dependent fractionation of isotopes. Okay, what does that mean? So temperature-dependent fractionation, this word fractionation means where a process preferentially chooses one isotope over another. And temperature-dependent tells us that what's going to determine, whether we choose one isotope over another is temperature, right? So benthic forams have a temperature-dependent fractionation with respect to oxygen isotopes, meaning that depending on the temperature of ocean water, the oxygen isotope composition of a shell that a benthic foram is growing will change depending on the temperature of the water that it's growing in. Specifically, what this means is that the shells of benthic forams that are formed in colder water have a greater abundance of oxygen 18 relative to 16 than benthic foram shells that are formed in warmer water. So when a foram is living in relatively cold water, the shell that it grows will be enriched in oxygen 18 relative to oxygen 16. This is a thermodynamic fractionation that's got to do with the different vibrational energies between oxygen 18 and oxygen 16. And we don't need to go into that level of detail, but this rule here that shells of benthic forams formed in colder water will have a greater abundance of oxygen 18 relative to 16 is a very useful thing to understand when we're trying to think about the figure that shows how the oxygen isotope composition of benthic forams changes through time. Okay, so back to this figure. This gray trend here, again, remember this is the oxygen isotope record of benthic forams. So if you can see, each one of these, this whole trend is made up of a whole bunch of individual data points. So they're little plus signs. And each one of these plus signs represents a single benthic foram shells that was dissolved in a lab and its oxygen isotope composition was measured. So this whole curve is made up of thousands of individual benthic foram shells. And so remember, the oxygen isotope composition of the benthic foram shells can tell us about the temperature of the water that they grew in. And we know that colder waters are going to make benthic foram shells that have a greater abundance of oxygen 18 relative to 16. And so that should lead to an increase in the delta 18O value, right? This is an increase in the abundance of oxygen 18 compared to 16. So that's telling us that since about 50 million years ago, there's a general trend towards more oxygen 18 present in these benthic foram shells. So that tells us that global ocean waters have been getting colder. Cool, right? But there is more to the story. So you might have noticed this abrupt change in the forams oxygen isotope compositions here between the Eocene and Oligocene at about 32, 33 million years ago. So there's an abrupt change in the isotope composition, but you'll also notice that there's also more scatter in the data after that time period, right? The whole curve gets a little bit thicker. Okay, so that's interesting. Why might that be? So let's explore the second way that oxygen isotopes are useful for telling us about Earth's climate. To understand the second piece of the puzzle, we're going to need to go back to thinking about our uneven distribution of heat on the Earth's surface and how that has implications for how oxygen isotopes behave at the Earth's surface. Okay, so recall that oxygen 18 is heavier than oxygen 16. It's got 2 extra neutrons. And that means that they're going to behave differently during processes like evaporation and precipitation of water. Okay, so remember that at the equator, we receive much more direct sunlight, and so the equator is warmer than the poles. That means that the equator is very prone to evaporation of seawater. So there's lots of evaporation of seawater at the equator, and that evaporation of seawater makes clouds. Because oxygen 16 is lighter than oxygen 18, it's going to be preferentially evaporated, right? So when clouds form, clouds that are evaporated water vapor from the world's oceans, when clouds form at the equator, they preferentially become enriched in oxygen 16. They don't have very much oxygen 18 because it's heavier than oxygen 16, right? It's harder for it to be evaporated. So that means that the oxygen isotope composition of clouds is very isotopically light. There's very little oxygen 18 and a whole lot of oxygen 16 in clouds. So because oxygen 16 is easier to evaporate, clouds end up having a very low oxygen 18 to 16 isotope ratio. We're going to always have this ratio of 18 over 16 so that we can keep things consistent here. but because oxygen-16 is easier to evaporate from the ocean, there's much more oxygen-16 in clouds. A larger denominator means that this is going to be a lower isotope ratio. The oceans, in contrast, right? The oceans have all this oxygen-16 taken out of them. They have it evaporated into those clouds. So the oceans end up becoming enriched in oxygen-18 because they've lost a lot of oxygen-16 to evaporation. So we know from our large-scale climate and weather systems, right, that air is constantly circulating in the atmosphere, and it's ultimately going from the equator to the poles, right? The uneven distribution of heat on the Earth causes air to eventually make its way from the equator to the poles as a way to redistribute heat from the sun. Okay, so that means that the clouds that form the equator are going to migrate towards the poles. Remember, so we've got the South Pole down here. So the clouds are going to migrate towards the poles. And on the way, those clouds are going to rain. Eventually, they will drop some of their water and rain back down onto the surface of the Earth. Now, just like oxygen-16 is easier to evaporate than oxygen-18 is, whenever you've got water vapor in clouds, if there's any oxygen-18, it's going to be the very first to go as rain, right? That oxygen-18 is heavier than oxygen-16. It wants to fall back down to the Earth. So when that water condenses, the water that's got oxygen-18 in it is going to condense first and fall back down to the Earth. Okay, so as air with water vapor in clouds moves from the equator to the poles, it becomes preferentially sort of depleted in oxygen-18, right? It just, first of all, there's not very much because it gets left behind during evaporation, and then any that is in there gets preferentially dropped as rain. So by the time clouds finally make it, to the South Pole, where it's cold enough that this, water vapor is going to fall not as rain, but as snow, that means that its isotope ratio, its oxygen to 18 to 16 isotope ratio is really, really, really low. Now that's really important because when snow falls at the South Pole, it lands on the ice sheets in Antarctica, right? And so that snow that has a very, very low 18 to 16 oxygen isotope ratio ends up getting locked up as ice in Antarctica. So the polar ice caps have very low 18 to 16 oxygen isotope ratios because that snow started out as water vapor at the equator, it evaporated, and it became progressively depleted in oxygen-18 as it moved from the equator to the poles until it finally fell on Antarctica with this really, really low 18 to 16 oxygen isotope ratio. Okay, so how does this whole process tell us about, Earth's climate through time? Well, if we recall the paleogeographic map that from 90 million years ago, we saw an ice-free Antarctica, right? There's no geologic evidence for the presence of ice on Antarctica about 90 or 100 million years ago, even though Antarctica was still sitting at the bottom of the Earth at the South Pole. Okay, so we know that as moisture moves from the equator to the poles, it becomes progressively isotopically lighter, right? It's losing all of its oxygen-18. It's almost entirely oxygen-16 by the time it gets here. And as it falls as snow and on Antarctica, eventually ice sheets will start to form. Eventually those ice sheets will grow and they'll cover the whole continent like they do today, right? But so think about what that's doing. That's taking oxygen-16 out of the oceans and bringing it all the way to the poles and locking it up as ice for a very, very long time. So the overall effect is to take oxygen-16 out of the oceans and store it in ice. So that means that the oxygen isotope composition of the oceans, if there's a lot of ice on the Earth, is going to be very enriched in oxygen-18 because all that oxygen-16 has been brought to the poles and dropped as snow. So the oxygen isotope composition of the oceans themselves will change according to the total volume of ice at the North and South poles. If there's a lot of ice, right, more ice at the North or South poles, that means that the oceans will have a higher oxygen 18 to 16 isotope ratio because that oxygen 16 has been removed by evaporation and transported to the poles, eventually to be deposited as snow and ice, right, stored in these ice caps for a very long period of time. So now coming back to this figure, you'll notice that at the Eocene to Oligocene transition, right, this dramatic change in the oxygen isotope composition of benthic forams, we see that this figure also indicates that right at this time is when Antarctic ice sheets appeared on Earth. So they were probably forming a little bit before that, right? There's evidence for intermittent ice sheets, but the geologic evidence for permanent ice sheets on Antarctica falls right at this transition between this period we call the Eocene and the Oligocene. And so that additional source of variation in the oxygen isotope composition of the oceans and therefore in benthic forams is what causes the curve to have a greater spread here, right? The spread sort of gets larger. This whole band is thinner back here before there were ice sheets because the only thing that was controlling this was the temperature of the ocean waters that the forams were growing in, right? But so now we have these two different controls making a little bit more wiggle room here in this curve. So to conclude, we've got these two processes that both change the isotope composition of benthic forams through time. First, we have a temperature-dependent fractionation where foram shells that grow in colder water tend to have a higher delta 18O value. And the second reason is that the more global ice we have, that tends to make oceans that have a higher delta 18O value. So those two phenomenon are both telling us that from about 50 million years ago to the present, the Earth has gotten much colder, right? It's gone from a point where we had tropical plants and cold-blooded animals living in the poles to now where we have ice sheets covering all of Antarctica and most of Greenland. So what processes can actually cause this dramatic change in Earth's climate? This is how we know that it has changed. Now we want to start talking about what actually causes it to change.